Hard to say, right? Oh, Zener diodes. First of all, let's talk about. So we have two categories of diodes so far. We have what we call rectifier diodes, which we covered fairly well, right? And then we have what we call small signal diodes. Unfortunately, these guys here are usually specified at around 60 hertz. They run fine on 50 hertz, but they're very low frequency devices. The problem is that we actually build a capacitor. So as soon as I come up here, especially reverse biased, so I come up here and have a lead here, and then we have a depletion region. So the depletion region acts like an insulator. And then these two right here would act like a plate. So what that means is anytime I've got capacitors and I put AC on them, we're going to have problems. And the formula is X sub C is equal to 1 over 2 pi FC. So this is the amount of opposition the capacitor has. So what happens is the frequency goes up, the opposition goes down. So rectifier diodes, we don't operate them at extremely high frequencies because they would start letting stuff get through them, right? You understand that? So we have these high frequency diodes. These are called small signal diodes. They have extremely low capacitance, but they're not designed to run on, they're not designed to rectify or get a lot of current out of them. We can use them for rectifiers, but these are going to be in the milliamp range and the nanoamp range, right? You understand that? But what we can do with these things is we can come up and do something like this. And you still see these used every once in a while. And this would be my output. These over here would be my inputs. Oh, I got them turned backwards. So. I'm not going to color them in, even though we're supposed to. So what we're going to do is over here we're going to say if I put +5 on this, this will equal to a digital 1. If I put 0 volts on it, then this is going to equal to a digital 0. Now, when we say 0 volts, we're talking about what I'm going to do is I'm going to put my common over here. So let's go common. So what would happen if I come over here and I put a 1 on all these guys here would do what? They'd turn off because I got 5 volts on both sides of them. So I got 5 volts on here, 5 volts over there. The diode's turned off, right? You understand that? So what would my output be? If I measured it with a nice big meter. It's got like 10 megohms worth of resistance. So basically it's acting like an open. What would my meter measure? Let's say this is a 1K ohm resistor. So how much current flow do I have to the 1K? I got nothing because it's 10 megohm. My 1K, if it's got no current, V is equal to I times R, so that's 0 times R. So what voltage would it drop? How much voltage would it drop? 0 volts. So that means if I got 5 volts on this side, I'm going to have what on this side? 5 volts. So my output would be 5, or it would be what we call a 1, right? Don't understand that. So let's say I come over here and connect this over here to 0 volts, which is a common. So now this cathode is pointing toward negative. This is pointing toward positive. The diode turns on. How much voltage is the diode going to drop? So what would my output go to now? We're not even concerned with the rest of them. About 0.7, but we'll say a 0. Yeah, it's going to go to about 0.7, so we'll assume 0.7. Since we can't do without that, it's going to equal to a 0. So my output would go to a 0.7. So if I've got all highs on my input, the output would be 1. If I put any 0 on here, the output would be a 0. Right? So what this ends up being, if I was to draw the symbol for this, this is a digital AND gate. So we can do logic with these things. We can do ORs, we can do ANDs, and then we can combine another element and we can do NANDs and NORs. So we have 5 basic logic circuits that we have. We have what we call an AND, we have what we call an OR, we have what we call a NOT. We can't do a NOT with this, by the way. We have what we call a NAND, and then we have what we call a NOR. What we can do with this circuit right here, we can do both those right there. So we can do logic with diodes. But we're not rectifying, we're doing logic, right? And so these would be the primary use for small signal diodes. So rectifier diodes, they'll do logic, but they would cost a lot more money. So I can look up a 1N914, which is a small signal diode, and I can look up a 1N4001, and it would cost, the 4001 would cost more, right? You understand? Because it's designed to handle a lot of current. These guys are not designed to handle current. They're designed to give us ones and zeros out. That makes sense. So that's why we have 2 categories. Unfortunately, they both use exactly the same symbol. So the only way you know if it's a small signal diode is usually its size. So small signal diodes are going to be what? Really tiny things. So when we look at the 1N914, it's a little old tiny thing. It's glass, right? You understand? Because it's not designed to handle a lot of current. It's designed to switch signals, right? That makes sense? So this is a TI, this is a typical VI. What does VI stand for? Voltage current for a regular diode. So what we see is on the forward bias part, this is going to start conducting. For silicon, it's usually around 4/10 right here. We call this the knee. And then once we get above the knee, so this is where we want to operate the diode at right there, right? Everybody okay? And we use about 7/10 of a volt, but we know that it can actually vary depending on temperature and also current. Now, when we reverse bias this thing, they show dots here. When we reverse bias this thing, eventually it's going to do what? It's going to break over. And it's usually a real high voltage, like 50 volts, 100 volts, 200 volts. It's a real high voltage because these things are designed to run as rectifiers, right? Or small signal diodes. But what we notice is that when it does break over, it maintains a fairly constant voltage across it. It just burns up. We can't see it because it does what almost instantly. It burns up. Are we okay? But what we're looking at is what's so neat is that if I had the ability to protect this thing, we can use this voltage as a reference. And that's what a zener does. So this is the symbol for a zener. So we pick up a different thing. So this is the symbol for a zener diode. And I don't know how I got the name Zener. I'm sure it was some guy or probably a guy because most of the men did that. that trade when all this was coming back. Somebody out there has probably got this name. I don't know how I got the name. A silicon PN junction, a Zener diode is specifically designed to work in this water. Breakover. Next slide shows the operation of the rectifier diode and a Zener diode. So what we're doing is that the Zener diode, the breakover voltage is going to be relatively low, right? On a rectifier diode or different small signal diode, the breakover voltage is going to be relatively high, right? Understand? Okay. So we normally operate. If you check a Zener diode with an ohm meter, it's going to check just like a regular diode. So you can't tell it's a Zener diode. The only way you can tell it's a Zener diode if you look up the part number. So we call this the Zener region. We call it the voltage meter. Now notice it stays fairly constant. It's not constant, but it stays fairly constant over a wide range of operations until you burn it up. And we'll look at how we can calculate that in a minute. Avalanche and Zener. So this is bad for regular diodes. Zener breakover is what we're designed to do. Zener breakdown occurs at a lower reverse voltage compared to regular diodes. The Zener has a very narrow. No, we call the breakover for a regular diode. This is what for just diodes. It's not called that. It's an avalanche breakover because it just avalanches and it does what? Avalanche even in mountains and snow is not good, right? Zener is we're designed to operate that. Now you got to understand we still got to protect our Zener. And what do you think we're going to protect it with? If I don't protect my Zener, and then I put it across a voltage, and it's set to break over at 5 volts, and I put 7 volts across it, it's going to bop it just like that. So what do you think we got to put in series with it? You got to put a resistor. You got to put a resistor. You got to put that resistor in there to protect it once it breaks over, and we'll look at that in a minute. As reverse bias is increased, the reverse current remains very small until it reaches what we call the knee of the curve. So we call this guy right here what? Yeah, we call this the knee. Breakdown effect begins at the knee. At this point, the current increases rapidly. The breakdown voltage remains essentially what? Constant. It's not constant. A Zener diode keeps an almost constant output across its terminal within a certain current range. If you put too much current through it, it's going to burn up, right? You understand that? So we have some things that we're going to look at when we look at the data sheet. One thing they're going to show us the knee current. They're going to call this IDK. Another thing, they're going to give us the test current. The test current is where the Zener voltage is established. And then we're going to learn what we call IZ max. What do you think happens if I operated above the maximum current? It's going to burn up because we're putting current through a voltage, right? You understand that? Anytime I put voltage through a current, it generates heat. So what we want to do is we want to operate that thing somewhere between IZK and IZ max. We try to operate it as close to this as we possibly can. And then we can move up a little bit and down a little bit. Right? Does that make sense? Okay? IZK and IZ max. IZ knee and IZM. But these are some of the data sheets. When we look at the data sheet, we're going to see this, we're going to see this, and we're not going to see this. This is not shown. But it's easy to calculate. Very simple. We'll show you how to do that. This voltage right here, by the way, we refer to this as VZ. So when I look at a diode, and a Zener, and it's got a 5.1, that's the rating, VZ. and then it's going to give an IZK. So IZT. So this is established as that, right? You'll understand that. Yeah. No, not at the knee, at its right here. So VZ is established at IZT, at Zener test current. So if I operate it below the test current, it would be, if it's rated at 5.1, it should be what? A little lower than 5.1, right? If I operated above it, it should be a little greater than 5.1. So if you have a real big current variation between the Zener, then it's going to vary, but it's not going to be that much. I mean, right here it might be, down here it might be like 4.7 volts, right? And up here it might be like 5.6 volts. So it's not going to vary very, very much between its regulation. That makes sense? So IZK, to regulate a Zener, must always be operated above what? IZK. Everybody understand that? And that's going to be given in the data sheet. IZT, the current flow where DZ is established. Circuit should be designed to regulate as close to this current as possible. IZ max operating above this current when family is observed. It's not given in the data sheet, but what they do is they give you the maximum power. So if they give you the maximum power in the data sheet, you calculate IZ max by taking I is equal to P over V, right? So over here, we're going to use the max power that's given in the data sheet. And then we're going to use VZ, and this will give us what? This will give us IZ max. So we have to calculate IZ max. Now, why do they do that? I don't know. It's just what they do. So what you're given in the data sheet, you're given the knee current, you're given the Zener current, test current, and you're given the maximum power that you see. When you look at them, you're given two things. If they talk about a Zener, they're going to say, okay, this is going to be a 5.1 volt, 1 watt Zener. So that's what when they give you the specs. So to get these other things, you'd have to actually look in the data sheet, right? That makes sense? Are we okay so far? Ideal, Zener is equivalent to a voltage source. Practical, Zener is equivalent to a voltage source in series with a very small resistor. The Zener impedance can be calculated by changing voltage divided by a change in current. The Zener impedance is usually given in the data sheet. It's specified as IZT, Zener test current on the Zener data sheet. It's specified at the data sheet. Are we okay? That makes sense? Usually we don't use that. In fact, we don't use it. What we're going to use is we're going to use ideal Zener, and then we're going to know that it's going to vary a little bit, right? You understand that? That makes sense. So if I got a 5.1 volt Zener, we're going to say 5.1 volts to do all our math. So this would be an ideal Zener. So we'll say it comes over here after has actually no leakage current, and then when it gets to it does it, and it's going to regulate it. I do. That's what we use because we, if it's really, really critical, an engineer might take into place all that other kind of stuff, but we're not there. All we're trying to do is just we're going to use ideal for all of that. And what laws are we going to use on this thing? Ohm's law and Watt's law. All we got to do is apply it to Zener. So this is the way they calculate ZZ. So they go over here around IZT and they do a delta Z. What is delta Z? Changing. So a change in voltage over a change in current is the way they calculate this. Now, this is given in data sheet, but we're not going to use that. ZZ top, right? Anybody? I was a ZZ top fan. Because I probably look like one. Y'all had never heard ZZ Top's music. You are today or really. And there's only three people. There's only three people in that band. A bass player, a lead guitar player, and then a drummer. So this is just an example. So what would VZ be here? So I come over here. I got a 50 milliamp, 50 millivolt chain. I got a 5 milliamp chain. So what would our calculated Zener resistance be? Be 10 milliohms. So you see this guy's got pretty low resistance. Are we okay? Questions? Lost anybody yet? Data sheet. So the Zener impedance, temperature rated at, power dissipation, we'll look at how the die rate should decrease by Zener test current, Zener voltage, and IZ max. So let's go ahead and look at a data sheet. We'll find on Blackboard. No, I don't have Blackboard anymore. Decrease by. And that's a term we use a lot. If you're in residential wiring or commercial wiring, you're going to hear that a lot. So we'll see at what Zeners we have, what data sheets for Zeners we have up here. So we use data sheets so much, you got a data sheet in front. This is 4700 series worth of Zeners. So this is all these go from 47, 28 all the way to 47 forward. These are 1 watt Zeners. There's your Zener power right there that we calculate out of max. This is what varies with the regulator, your Zener voltage. So these guys vary, but it says, okay, so this is what we're talking about die rate. So these guys are rated at 1 watt, but this is at what temperature? 50 degrees. So anything below that, we would probably be able to get a little more than 1 watt, but that's what we rated at 1 watt. If we operated above 50 degrees, then we need to do what? We need to die rate it by what? 6.6 milliwatts for every degree above 50 degrees. Y'all understand that? Yes or no? So y'all got the data sheet up? Because I'm fixing to bring up a PowerPoint. I'm not going to save it. I'm just going to make it one. Okay. So it says, okay, at 50 degrees centigrade, it's rated at 1 watt, right? Okay. And then it says we're supposed to die rate it by 6.25 milliwatts per degree centigrade, above 50. So let's say I operated at 85. I operated at 85 degrees. So I'm going to say 85. I'm going to subtract 50 from that. That gives me what? 35. I'm going to take 35 and multiply it by 6.65 milli. What does that give me? Oh, 35, Rich. 35. Yep, because that's what it says for every degree centigrade, right? Above 50, right? So what does that give me? What's that? Milli, or 233. 233 milliwatts. So I'd take 1 watt, right? And I would subtract 0.233, and now that would be the power that the Zener would be able to power within carry out. Yeah, because, huh? Yeah, this is what it's rated at. So it's rated at 1 watt. We die rated it by 233 milliwatts because we're operating at 35 degrees above its rated temperature, right? Okay, so what would that give us? Yeah, so now we've dropped down to 767 milliwatts. I'm sorry, 767. I don't know where I got my period at, milliwatts. Well, that's what we mean by die rate. It means decrease by, right? So it's, everybody okay? That makes sense? Then we have to die rate it depending on the length of our leads. Power temperature die rating curve. So that means if you have a lead that's, let's see, so 1 inch, so you have 1 inch extended out beside that thing, then you got to die rate it according to this temperature chart, right? 3/8, 1/8, and 3/8 depends on where you can do it, right? You understand that? That makes sense. So what does it mean? What do you notice right here? What does it mean? Well, the shorter the lead, the faster it's going to get rid of the heat and get it down to the circuit board. Your circuit board has got all these power, these lands and everything on it. Those things are made out of copper, and copper is a really good heat, dissipates heat real well, right? So what they're saying is the shorter you can make those leads, the better it dissipates the heat. So it don't have to travel all the way down the leads to get into the circuit board. That make sense? This is the guy we're very concerned with. So what Zener do we want to look at? So here's our VZ. Here's the part number. So here's our VZs at IZT. You understand that? Here's our part numbers. So if I had a 1 in 4738, it would be rated at 8.2 volts. That makes sense? You okay? Then it gives me the Zener test current, which is 31 milliamps. It gives me my Zener impedance, which is in ohms. There's a note there. It gives me IZK, so we're interested in this because this is our watt. That's our need current. We're not concerned with the leakage current. And surge current we can handle up to this. So the two main things we're going to look at is what? VZ, and we're going to look at IZK. And then we're going to calculate IZ max. That makes sense? So what would I be, if I'm looking at this guy right here, what would IZ max be for this 8.2 volt Zener? Oh. So IZ max would equal to, I gotta figure out what I'm doing to make it zoom. So IZ max would be equal to 1 watt divided by 8.2 volts. So there's, what's that? I didn't hear you. 122 milliamps. 122 milliamps. Are you okay there? Questions on there? We okay?
What's on the end?
122 milliamps.
That is 122.
I guess. I didn't do the math.
No, I can read it. Like,
Huh? Yeah, maximum wattage over the voltage, right? I'm sorry. Yeah, I equal P over V. So are you okay there? That make sense? Questions? So we looked at all these, right, in the data sheet. You okay on those? Well, I had a blank slide in there. All right, this is the data sheet. Zener regulation, Zener diodes can be used for voltage regulation in low current applications. It takes a varying DC unregulated and keeps it relatively constant, even though your input voltage is changing and your output currents are changing, right? Zeners can only work over a set range of currents. We got to operate it. We cannot operate it below the knee or toward, and we can't operate it above IZ max. Everybody okay? Below the knee. And this is just regulation. The series resistor, any voltage applied to the Zener that is above IZK will be a what? Short circuit. A resistor that is connected in series with a resistor that we're going to generically call RS is required to draw the difference between the unregulated and the regulated voltage. Calculating the size of this resistor is critical to the operation. Y'all understand that? Well, that's good. So let's take a break. So this is a basic Zener regulator. Are y'all listening? Yes, sir. So this is a positive supply. Zener is put in reverse bias. Zener normally operates in reverse bias. If you forward bias it, it drops about 7/10 of a volt. I've never seen a Zener made out of germanium. So every Zener I've ever seen has been made out of silicon.
So you can standard operate these for a Zener
reverse bias to make it regulate. In order for a Zener to regulate, it has to be reverse bias. Regulating the voltage. Not the current, it's the voltage. Later on, when we get into bipolar transistors, I can show you how we can make current regulators. Here, we're going to use it to regulate voltage. So we'll let the voltage change. And when we talk about a regulated power supply, what does it mean? Well, it means things can vary, but the output will stay the same. If it was perfect, but there's no such thing as a perfect regulator. Even regulated power supplies gives you what they call a percent regulation. I don't think these do, even though they should. So this power supply says it puts out 20 volts at 3.25 amps. And it don't tell you percent regulation, but I guarantee you that's basically an average, right? You understand? It could be pretty close on this guy because this guy probably represents almost the same load all the time, right? So this is a standard Zener regulator. We have a resistor that we're going to generically call RS. In the real world, it might be called R53. But here, just for calculation purposes, we'll call it the series resistor. And what's the function of RS? Yeah, but that's not what I was looking for. So its function in life is to drop the difference between the unregulated voltage and the regulated voltage. Unregulated. That's its function. You always got to have more unregulated than you have regulated, right? You understand? So over here, we got all this garbage going on like this. So if I was to look at this with an oscilloscope, we're going to have this, right? You understand? And this is going to be riding above 0. So we're going to regulate. Worst case scenario, we got to regulate below that trough right there. Always. If that trough ever drops down, if you drop down below VZ, then it's not regulating anymore. So to regulate, or unregulated, has always got to be greater than the what? Than the regulated out. That makes sense. So I can't regulate, I can't have a 5.6 volt Zener and only give it 3 volts over here. If I put 3 volts over there, we never break it over and we get 3 volts out, right? You understand? It's varying all the time. So 5 over here, I might have this trough down here, might be 7 volts. And I regulate at 5, right? You understand? So now, and this would be the worst case. So we're going to have to make sure that when we choose the capacitor, that we choose that where that trough never gets below the Zener voltage. And then we're going to connect our loads over here on the right. So the loads are going to be in parallel with the Zener. So if the Zener's dropping 5.6 volts, it's connected in parallel with the Zener, then what's the load going to drop? Voltage in parallel is what? The same, right? You understand that? So that means if I come over here and put a resistor right here, this is what we'll use right now. If I put 5.6 volts across the Zener, then this guy right here is going to drop 5.6 volts too. And that's the way it regulates. So we put the load in parallel with the Zener.
That's all done.
If you want it, I mean, I can't say all. You very seldom hear me say all because some engineer will come up with another method. Because we use Zeners for different things. We use it to eliminate voltage spikes. So I've seen Zeners hooked up back to back like this. And then they'll come down here and take another Zener and hook it up back to back. You'll see this a lot. And what it's there is that it clips off voltage spikes, right? You understand that? So anything above whatever the Zener's rated at, plus 7/10 of a load, it just clip it off.
Like a regulator.
Well, that's what a Zener is. What is a Zener? A regulator? That's a voltage regulator, though, right?
So it's still not considered a load.
What's that? The diode is considered a diode. A diode is never a load. A diode is in there to turn AC to DC, or it's in to provide a regulated voltage. The diode is not the load, right? This is what I'm trying to load right here. So this computer is my load, right? You understand? All the electronics is in here is trying to give me a voltage for my load. So this is considered the power supply right here. This is my power supply. But what we've just done is we're going to come from this, right? So what we did back up here was we started off with this. We started off with a transformer, right? Started off with a transformer. Of course, we're going to plug this into AC or whatever. It might be hardwired. That's where we started at. What's a transformer? It's a power supply. It's a power supply, but it gives me AC. Right? You understand? Then we came up and added what? Then we added our rectifiers. I'm still working on the power supply. Now we don't have an AC power supply anymore. We got a DC power supply, but it's pulsating, right? You understand? Then what did we add? We added a filter. This is still the power supply. We're still working on a DC power supply, right? You understand? What does the filter do? It turns pulsating DC into unregulated DC, right? And then what are we working on now? We're working on the regulator. And then that's my power supply. So this is my power supply. Then what do we connect to power supplies? We connect loads. What do we want it to run? Do we want it to run a motor? Do we want it to run a stereo? Do we want it to run this? Do we want to run that? Do we want it to run a computer? So here's my power supply, right? You understand? What's its function in life? To take AC and give me regulated DC. And it's got a lot of junk in there, right, to do that. This is a switch mode power supply. We need to make sure we go over these a little bit too. But that's the function of these things. To take what? DC, take AC and give me some form of DC. And this is a regulated power supply, which means we can vary the loads, right? Or the input voltage can change over a range. So what we're doing now is we're still working on our power supply. So no, it's not a load, it's part of our what? Power supply. And what it's going to do is it's going to establish a voltage that stays fairly constant as long as we operate it above what? IZK and below IZ max. If I get into my knee, I go out of regulation. If I go above IZ max, then the Zener's probably going to do what? Going to burn up. That's all we're saying is just figure out how we're going to operate that. Then I got to put that resistor, because I've got unregulated on this side, I got regulated on that side. This guy here's all over the place. And so that resistor is what's dropping the difference between the unregulated voltage and the regulated voltage. And what determines the amount of voltage a resistor drops? And the resistance, the size of the resistance and the amount of current flow we put through it. So if I choose a resistor that's too big, it's going to drop too much voltage. The Zener don't have 5.6 volts over there anymore, and it goes out of regulation. If I choose a resistor that's too small, we go above IZ max, and it'll do what? It'll burn up. So we got to choose that resistor pretty, and we're going to use Ohm's law. We're just going to figure out what R is equal to what? V over I. All we got to do is figure out what V I'm going to use and what I'm going to use. Are we okay? No load, full load. When there's no load, resistor, no load, we don't have a resistor out there. The load current is approximately 0. All the current flows through RS must go through the Zener. What's so neat about the Zener is the Zener dynamically adjusts its internal resistance. Dynamically. We could regulate, if I could sit over here and take a potentiometer or a rheostat, I could make it act like a Zener, but it would be almost impossible for me to do that, right? That makes sense. When there's a connected load, the total current through RS is shared by the what? The load in the Zener. To keep the current through RS constant as the RL increases or decreases. So if the load current is constant, RL is decreased, the load current goes up, and the Zener current goes down. Do y'all understand those things? Okay, so let's say, let's go back to this drawing right here, and let me erase all this. Okay, so we're going to use fixed voltages. Okay, but we realize it's going to change, and we'll use some that's pretty high. We'll see if we're not going to deal with IZ max. We're just going to see what's going to happen. So let's say I have a 5 volt Zener. Okay, and let's say I come over here and put 7 volts on there. How much voltage is RS going to have to drop? 2 volts. All right. So let's say I put a load out here that requires, at 5 volts, it requires 200 milliamps. That's not going to work. And let's say we come over here, and this is, let's do it this way. Let's say it requires 100 milliamps. In this right here, I make a 100 ohm resistor. So how much current would be flowing in the circuit? Since RS is a series resistor, all current in the circuit between the Zener current and the load current has to flow through RS. So how much current is flowing through RS? How much current is flowing through RS to make it drop 2 volts? It's 100 ohms, guys. So my total current in the circuit would be equal what? What's that? Well, I know 1K would be, no, we got to make it smaller. Let's make this 10 ohms. We got to have more current than we got over here. So that would, what would that be? Should be 200 milliamps, right? Right?
Yeah.
Okay, so 200 milliamps. My load needs 100 milliamps. My load needs 100 milliamps. I've got 200 milliamps through my resistor. How much current flow is through the Zener? According to Kirchhoff current law. I have 200 milliamps right here. I got 100 milliamps going this way. How much current flow do I have going through the Zener? Huh? 100 milliamps. Okay, are you okay? That makes sense. Okay. So let's say my input drops down to, let's say it drops down to 6 volts. Then how much is this dropping down? Five volts on this side, guys. 6 volts on that side. 5, 6. So how much is it dropping? Okay. It's 10 ohms. What's going to happen? This is still a bad example. Okay, 100 milliamps. So how much Zener current do we have? We just went out of regulation. How much Zener current do I have? 0, right? So let's go back and redo this. So let's use, we're using Kirchhoff's law. So let's use a 10 ohm resistor, right? I'm gonna hook a load over here that requires what? 100 milliamps. So let's use, let's say 10 volts, and let's say we're going to start off with 10, and then let's drop down to 7. So at 10 volts, and this is a 5 volt Zener, so that's VZ is 5 volts. Okay, so I start off at 10 volts. How much voltage is going to have to drop across RS? Okay, 5 volts. Okay, 5 volts. So how much I is going to be through RS? So IRS is going to be 5 divided by 10. That's going to be equal to 500 milliamps. My load is required what? 100 milliamps. I have 500 milliamps right here. So 400 milliamps is going to flow through the Zener. Don't understand that? Okay. So let's say my input, it's unregulated. Let's say it drops down to 7 volts. So I could calculate my Zener resistance at that point. So Z would be equal to, R is equal to V over I. So it's going to be V divided by 400 milliamps. So what would my Zener resistance be? What's that? Okay. All right. So let's say we come up here, my input drops down to 7 volts. So if it drops down to 7 volts, it's 7 volts, then how much is my resistor going to have to drop? 5 volts on this guy, 7 volts on this side, 5 volts on that side. How much did it have? 2 volts, right? Yeah. So then I'm going to say IRS would be equal to 2 divided by 10. It's going to be what? 200 milliamps. What's the current through my load? 100 milliamps. That's my load, right? You understand? So now this guy drops down to what? It drops down to 100 milliamps. Now, how did it do that? Well, it literally dynamically changed its internal resistance. So now my Zener resistance would be equal to what? 5 divided by 100 milli. And what's going to be now? Yeah, 50 ohms. So we're looking at the Zener resistance is dynamic. It's constantly changing to adjust for what the demands of the current, the demands of the load and the change in input voltage. And it's doing this dynamically. You don't have to do anything. It's going to try to maintain its output, its voltage, as long as you operate it above what? A current above IZK, and as long as you operate it at a current below IZ max. If you operate it below IZK, it goes into the knee and it goes out of regulation, right? You understand? That's what happened a while ago when I just threw numbers up there, because we ended up with zero current flow through the Zener. If I have zero current flow through the Zener, it goes out of regulation, right? You understand that? So for the Zener to regulate, we got to regulate somewhat. We got to have it what? We got to operate it above IZK, and we got to operate it below IZ max. And it's going to constantly change its current. It's going to constantly change its resistance. So let's say I come over here and I put 7. Let's say I come over here and I put 5. Let's go to 7 volts again. So 7 volts, that means RZ, that means IRS has got to conduct 200 milliamps. So let's see what happens if my load current changes. So let's say we need more load current. So I come over here and I say, okay, now my load needs what? Let's change it just a little bit. So let's say now my load needs 50 milliamps. So guys, what's happening? Well, we need 50 milliamps right there. We got 200 milliamps right here. We need 50 milliamps right there. Kirchhoff's law says the sums of these currents have to equal each other, right? So they see my Zener current is going to go up to 150 milliamps. Automatically, you don't have to do anything, right? You understand? You don't have to do anything. So we can come up here. Let's say my load needs 150 milliamps at 7 volts. So what happens? So my voltage is at 7 volts, right? You understand? 150 milliamps right here. I have 2 milliamps. So my Zener current goes to 50 milliamps. Do you have to touch anything? Do you have to do anything? No. So what happens is that your currents, they operate opposite. So as your load current goes up, your Zener current goes down. If your load current goes down, your Zener current goes up, right? You understand? What about my input voltage? Well, if my input voltage goes up and my load current don't change, then if my input voltage goes up, my Zener current automatically goes up. If my input voltage goes down, my Zener current automatically goes down. So Zener current varies inverse to what? To load current. It varies in the same direction as your input voltage. And it does this what? Automatically. Dynamically. So yeah, I could come up here and I could put this guy at 12 ohms, or I could put it at 50 ohms when the input voltage changes, but that input voltage is changing constantly, right? If the input voltage is the same and I've got a filter, then it's constantly changing. It's changing what? It's changing every 8.33 milliseconds. It's changing, right, for a full wave. But the Zener automatically compensates for that, as long as I give it more input voltage than it's supposed to regulate. And we don't want to give it a lot, because if you do, then this power, this resistor, what are resistors rated in? What's the two main things? Don't say tolerance. Everything's got a tolerance. So every component we have has a tolerance. Besides for the tolerance, what are resistors rated in? If I buy a resistor, if I look up a resistor, what's it rated in? Ohms and, guys, this is something y'all should know. Ohms and what's the second thing? No, they're not rated current. Watts. There's the two things they're rated. And then a tolerance. Zeners have a tolerance. Right now, we're not talking about that, and we need to go back and look at that in a second. So Zeners, it might be a 5 point something volt Zener, but it's going to have a what? A tolerance. Resistors have a tolerance. Capacitors have a tolerance. So just about everything that we do is going to have a tolerance to it, right? You understand that? But when I buy that thing, I got to make sure I'm going to have to make sure I'm going to try to get the resistor I can use, right? Y'all understand that? With the lowest wattage rating I could possibly choose, because the cost of the resistor varies at size. So let's say when this one guy uses a 10 watt, 10 ohm resistor, and this other guy uses a 10 ohm quarter watt resistor, who's going to have to charge more, not like make as much money, right? The guy that's using the 10 watt will work fine. But what you're doing is you're just doing what? You're just wasting money. The F4 Phantom, it could fly in excess of Mach 2, but the jet engines they put in there, it run I forgot, Pratt and Whitney's, could actually run the plane faster than the airframe could handle. So they were actually wasting money. They never could run the engines on the F4 full blast because it would tear the airframes up. So they was wasting money. It's like me going out and getting a 1,000 horsepower motor and putting it in a Volkswagen, right? So we're trying to choose a resistor. We're trying to choose a Zener that's not going to burn up, right? Give us a regulated voltage. And we're going to try to choose a resistor at the lowest possible wattage rating I can get without it doing what? Burning up. So guys, what happens? When is worst case? So let's look at that. So this is a good test question. So the Zener current varies opposite of the load current, right? So if the load current goes up, Zener current goes down. If load current goes down, Zener current goes up. Everybody understand that, right? It varies in the same direction as our unregulated voltage. If our unregulated voltage goes up, Zener current goes up. If our unregulated voltage, Zener current goes down. Did I say that right? If our unregulated voltage goes up, Zener current goes up. If our unregulated voltage goes down, Zener current goes down. Now what's going to happen? That's if the other thing is held constant. So what's happening is if our load changes and our input voltage is changing, these guys are going to be all over the place, right? Yeah, so it's just like when we talk about Ohm's law and we say they're directly proportional or indirectly proportional, it means something has to be held what? Constant, right? You understand that? So if load current is constant, then Zener current varies in the same direction as our unregulated voltage. If our unregulated voltage is held constant, then it varies opposite of the load. So what do we got to design? What do we got to design that resistor there to drop? Yeah, we're going to have to choose a resistor. And of course the formula we're going to use somehow, the formula we're going to use is R is equal to what? VR. That's the formula. But we're going to have to compensate or figure out what are we going to use for V and what are we going to use for I. What you're trying to do is you're trying to make sure that this guy never goes below what? IZK. So if my input voltage goes up, I move above IZK. Right? You understand? If my input voltage goes down, I move toward IZK. So we want to make that thing always be above IZK. So what voltage are we going to use to calculate that resistor? We're going to use the minimum voltage or the maximum voltage. We're trying to make it move this way, guys. So we're over here on this. We're not looking at the other one. Here's IZK. Here's IZK. And we're trying to operate it this direction right there and not burn it up. And we're talking about our input voltage. Our input voltage. Huh? We're going to use the lowest. So we want the lowest voltage that that resistor would ever drop. Right? Now what are we going to use for current? Well, over here, if my load, it varies in the opposite direction. So if my load current goes up, Zener current goes down. If my load current goes down, Zener current goes up. So what are we going to use for our current? We're looking at IZ, we're looking at my reverse current right here, right? Y'all understand that? We're trying to operate it above IZK. If my load, this is load right here. So if my load goes up, if my load current goes up, Zener current goes down. We're moving toward IZK. If my load current goes down, Zener current goes up. We're moving the way we want to do it, right? You understand? So what are we going to use? Are we going to use the minimum load current or the maximum load current? If I use as my Zener, if my load current goes up, right? You understand? If my load current goes up, my Zener current goes down, which means we're moving toward IZK. We don't want to move toward IZK. We want to move away from it. Right? You understand that? Okay. So we're going to use our what? We're going to use our minimum load current to move it away from IZK. And we're going to use our what? Maximum voltage to move it across RZ, move it away from IZK, right? Does that make sense? Everybody okay now? So what do I need to know? So let's say my input is varying from, let's say it's varying from 10 to 7 volts. Okay. And over here I've got a 5 volt Zener. And then let's say my load current is going to be anywhere between 10 milliamps and 50 milliamps. So what voltage am I going to use? So R would be equal to V. What voltage am I going to use? That's what most people think, but that resistor is high, it's the minimum voltage that resistor is going to drop. That if that resistor drops 7 volts, how much voltage do we have left over from our load? 0. So what voltage are we going to use? How much, to calculate the size of the resistor is V across the resistor divided by the current flow through the resistor. So it's never going to drop 7 volts. If it drops 7 volts, guys, how much voltage do we have left? 0. Yeah, that's what we got to figure. We got to calculate the size of the resistor. It's not this, and it's not this. It's how much voltage that resistor is going to drop. So what voltage are we going to use? Yeah, y'all gonna kill me. I'm gonna use 2 volts. That's the minimum it's gonna drop, right? Minimum it's gonna drop. We figured out we're gonna use the minimum voltage, right? That it's gonna drop. 7 minus 5 is what? 2. Okay. And what's my load current gonna be? My load current I'm using between 10 and 50 milliamps. What's that? I'm trying to let y'all come up with this formula. Because if y'all come up with it, then we're going to do this, right? So we're going to look at load current. And we want to move it away from IZK. So here's IZK right here, right? Here's the knee, and here's IZK right here. And we're trying to make it move in this direction right there. Okay. So what happens is as the load current, this is the load, this is the load current, and this is Zener current. As the load current goes up, Zener current goes down. As the load current goes down, Zener current goes up. We're trying to make our Zener current move in this direction right there. So this is load current right here. So if load current goes down, so I load goes down, Zener current goes what? I need to draw these the other way because this is the direction we want to do. So on this one though, the arrows are backwards because Zener current is going up in this direction right here, right? Y'all understand that? Yes or no? Because here's IZ right here. Here's 0. So this is direction over here we want to move right there. So what's that? When's that going to happen? So if load current goes up, Zener current goes down. So we're moving toward the knee. If load current goes down, Zener current goes up. So we're going to use the minimum current. So you're 10 milliamps. But we're going to come up and add a little bit to it. Okay. So what we're going to do is that this would put me right here. We want to operate above IZK, above the knee. So we're going to add to this IZK. That's the only difference between so that would give us our total current, right? Everybody understand that? So where are we going to find IZK at? So let's look at the data sheet and see if we got a 5-volt Zener over there. If we don't have a 5-volt Zener, then we'll just use the 5.1 just to get an idea of it. So y'all got the data sheet up? Do we have a 5-volt Zener? Do they have a? Well, that's what we'll use then. So what size R are we to use? So what we're going to do, this is going to be, R is going to be equal to 2 divided by 10 milli plus what? What's IZK? What's IZK for, what's that? Really? Is that right? 1 milliamp? Huh? Okay. So I'm going to add 1 milli for that. And then I'm going to come up here. So my size of my resistor, RS, would be equal to 2 divided by 11 milli. What would that give me? Two divided by 11 milli. What's that? Now the problem is there's no such thing as 180. Well, I could make a 180 ohm resistor. I'd go out and get a rheostat, or I could get a pot and wire it as that. Pots cost about $5 a piece. Resistors cost about cents apiece. So what would we do with this? Would we go to the next, would we go up or would we go down to the next standard value? So we go down or would we go up? Fifty chance. What do you say, Damon? What do you say, Joe? Huh? What do you say? What do you say, Joe? Okay, so if we go up, we move toward IZK. If we go down, we move away from IZK. So we're always going to go down. Always. If it felt on a 2.2K ohm resistor, I would always go down to the next standard value. Everybody okay? And then I would check the tolerance. If my tolerance turned up to be greater than 181 ohms, I would go down one more value. Right? You understand? So we check our tolerance. So let's see what size resistor would I use. Anybody know what standard resistor? Might be. Probably not. So where are we going to find this information at? Probably on Blackboard. Probably in reference material. Reference material. We calculate 181 ohms. Everybody okay there? Standard resistors. We give 5 or 10%. That's the book I got it is, but you can't hardly find a 10% resistor anymore. Just about what we have now is 5% would probably be the minimum you have. That would be the cheapest too. So here's 180 ohms. We got 160 ohm available. Would 160 work? Well, it's 5%, so would it work? So we calculate, we'll multiply it by we'll multiply it by what? 1.05, right? Understand? They'll raise it by 5%. So take 160 multiplied by 1.05. What's that? I'm sorry, 1.5, right? No, 1.05. 1.05? What's 168? So we'll be fine. What do you mean? It's in reference material. You could look it up on the internet and say standard resistor. Inside reference material, standard resistance. So you can buy them, you could buy 1%ers, but you're going to be paying a lot of money. We don't really need to do that, right? You understand that? We okay? So we wouldn't use this one, right? Because if we multiply it by 1.05, it would go over 181. So we always do what? Always round down and check the tolerance. And we'll use 5% resistor. Are we okay? That makes sense. You okay? So what would be the wattage rating of the resistor? When I buy a resistor, I just can't buy a 160 ohm resistor. I have to specify what? The wattage rating. So what wattage rating would I use? I could use a 10 watt, but I'd be spending a heck of a lot of money. So what wattage rating would I use for my resistor, okay? I think I lost all my math. Somebody give me an idea. So what's our input voltage changing between? Huh? 17. And we're choosing 100 and what? 60 ohm resistor. So what wattage rating do we need? And we're using a 5 volt Zener, even though we chose a 5. So what's the maximum volt? So it's gonna, when it's dropping its maximum voltage, it's just gonna dissipate its maximum power. What would be the maximum voltage that thing would ever drop? The resistor. The maximum voltage it'll ever drop. Be 5 volts, right? So I would use PR would be equal to 5 squared over 160 ohms. That's not 50, that's squared, yeah. It's squared over R. That's why it's nice to know the power point. Yeah, so quarter watt would be fine. In fact, we probably would use a half watt, but this is 250 milliwatts or quarter watt resistor.
All right.
Are we okay? So what's our standard wattage ratings for resistors we can see? What's the smallest? Yeah. Standard wattage ratings for actual lead resistor. Y'all don't know that? It's an eighth of a watt, then a quarter watt, and then a half watt, then 1 watt, then 2 watts, and then it jumps all over the place. You can tell by the physical size, right? The wattage rating. Of course, if you buy them. Are we okay? So I could use a half watt, but it would cost me more money than a quarter watt, right? You understand that? But if I use an eighth of a watt, what would happen? It'd burn up, right? So what we're trying to choose is we're trying to choose the smallest as close as we can. If I choose one too big, then it'll go out of regulation. If I choose one too small, then it'll exceed IZ max. Now let's say if we're going to exceed IZ max. So let's see, what would be the maximum current that would ever flow through the Zener? So what was my load currents we were doing? I lost all my writing. Was it 10 and 50 milliamps? So when would my Zener current be maximum? Yeah, we got to do 2 things. When my input voltage is maximum and my load current is minimum, right? So my Zener. So what I would do is I would come up here and calculate the maximum current through my resistor. What would my maximum current through my resistor be? How'd you come up with that? Now, what would the maximum current through that Zener ever be? I mean, I'm sorry, through my load resistor. This guy's telling me a lot because the difference, the current that flows through the Zener is the difference between what goes through there minus this right here, right? If I can do that, then I know what my Zener is. So when would the current flow through RS be maximum? I is equal to V over R, guys. We know R is going to be 160, right? You understand that? So when would the current flow through the resistor be maximum? When would the Zener current, when would the resistance current be maximum? What's the maximum voltage that guy will ever drop? Don't say 10 and don't say 7. Okay, so the maximum it'll ever drop is 5. What size resistor do I have? Okay, I chose a 160 ohm resistor. So the maximum current I'll ever get through that guy, as long as my power supply is working between its limits, would be what? 31.2. That can't be right. So over here we use 10, 50. Is this what we use over here, 10 and 50? Well, there's no way in the world this could come up and be, there's no way in the world if we did everything right, this could be 31 milliamps. Because I got to get at least 50 over here. So how could we have a maximum current flow of 31 milliamps when I got to have a maximum over here of what? 50. So what does that mean? Something ain't right. So what does that probably mean? Not the low currents, because the low current was given as a design, it was given as a design feature, right? You understand? So the 160 ohm resistor can't be right. Somehow we did something wrong. Because 5 divided by 160 is at 31 milliamps. Okay. So we just, y'all understand why it can't be right? Yes or no? Why? Yeah, the maximum current through that resistor, it's a series resistor, cannot be lower than this rate. Right? So let's figure out what we did when we calculated our 160 ohm resistor. So what did we do? We choose the maximum at the minimum current. Is that what we did? So y'all look at the formula sheet. Make sure I did that right. So we're looking at Zener regulators on our formula sheet. Let's say minimum voltage over the maximum current. Let's say minimum voltage over the maximum current. Is that what it said? I think that's what we did. I think we did. So that's what we did wrong. So this would be 5 over 50 milli, 51 milli. Where'd the 51 milli come from? Plus IZK. Yeah, because this goes down. This is right. Minimum voltage for the maximum. So I gave y'all the wrong formula.
So we didn't know, we multiplied that bottom part to add it up together. Is that what we did wrong?
No, what we did wrong was we used the minimum voltage over the minimum current. It's supposed to be the minimum voltage over the maximum.
What's the minimum voltage?
What's that?
Minimum voltage.
Yeah, I'm sorry. The minimum voltage over the maximum current. I got this formula over here in my head, but that's the way we'll calculate the power. The minimum voltage over the maximum current. Yeah, that's going to make a lot of difference. What's that? So I think we use the minimum voltage over the minimum voltage over the minimum current, but it's the minimum voltage over the maximum current. Okay, so what does this come up and give me? Okay, so what size are we going to use? Okay, 30.
No.
We should have a 33 in there.
Yeah, 36, 33.
So what we'd do first is we would try the 36 because we go down one, right? So we're going to say 36, and then I'm going to say times 1.05. What does that give me? Okay, so we can use that, right? Now, what are we doing this for? Yeah, it's giving us the upper tolerance. We're not concerned with the lower tolerance. We're concerned with the upper tolerance, right? Okay. All right, so now it makes sense. Now let's calculate the power of the resistor. There we go. We're going to use what?
Right.
Well, we can use two formulas. We can use V squared over R. So I could use I squared over 36. What's that?
694.
So we could use a 1 watt Zener there, right? That would be the minimum. We could use a 2 also. Everybody okay? Okay. Now this is where we came into problems. It's calculating our Zener power. And so here we're going to use V times I. So we're going to use the wattage, the voltage on the Zener, right? Times the maximum current that would ever flow through the Zener. So what would be the maximum current that would ever flow through the Zener? How'd you come up with that? So what I'm going to do is I'm going to calculate the maximum current flow in the circuit. And this is where we went wrong a while ago. So I'm going to take 5 volts and divide it by 36, right? What does that give me? Milliamps. Okay. And then what I'm going to do is I'm going to say 139 minus 10. Because the Zener current is the difference between this current and this current, right? So the Zener current is maximum when the load current is minimum. So it's going to give me 129 milliamps. So times 129 milliamps. So the power of my Zener would be equal to what? Yeah, milliwatts. So 1 watt, we wouldn't burn it up. By the way, if I chose a 1 watt Zener and I calculated it and it came up to be against 1 watt, then what I would do is I would find a 2-watt zener that gives me 5 volts, right? Does that make sense? So that's the math, guys. What laws did we use? Ohm's law, Kirchhoff's law, and Watt's law. Where'd y'all learn those at? Well, you were taught them in DC. Whether you learned them or not, I don't know. The percent regulation is calculated by using the difference in the zener voltage at minimum load and maximum load. Answer multiplied by 100 to convert the continuous current should carry. One of the things you get when you specify a power supply, you calculate what we call its percent regulation. There's no power supply that has 100% regulation. I don't understand that. That means it would be perfect. And if I'm not perfect, there's no way in the world this is going to be perfect. Don't need another break? Okay, so our input, the minimum input is supposed to be what? 7 volts? And what size resistor did we end up choosing right there? 36 ohm. Okay. And then we'll adjust this. So I'll adjust this with R. So if I hit shift R, it goes one direction. So right now it's set at 50%. So we'll turn on the simulation and see what our meters say. What's that? Thank you. So we were definitely out of regulation, right? Also, what we need to do is we'll grab a voltmeter and we'll put it across our load. And we don't have to put one across the zener because whatever's across the load is going to be across the zener, right? And now we'll turn on our simulation. So ours is a little high, 5.1. We got 11 milliamps. What do we need? What do we need? What's our minimum current? Like 10, right? Oops, went too far, Rich. Got carried away. We're doing this through I gotta be real slow because we're doing it through the network. That's probably gonna be about the best we can do. So notice, as my zener current goes down, as far as my 2.88 milliamps into it, I've got 10 milliamps going toward my load, and then my should be the sum too, right? So if we come up and raise the input voltage, if everything works right, this right here should stay constant, and the zener current should go up. So we'll change this over to 10 volts. Is that 10 is our maximum? So notice this guy here stayed about the same, right? This guy here stayed about the same. This guy here went up. Right? So that means the zener resistance had to be what? It went down. So let's drop back down to 7 volts. And then what we're going to do is we're going to raise our load current. What's our highest load current? What's that? Now Now notice the intercurrent is going down, right? Load current's going up, the intercurrent's going down. That's probably about it. Well, not bad, Rich. But notice if the load current went up, the intercurrent automatically did what? Went down. If load current goes down, the intercurrent automatically goes up. If input voltage goes up, the load current don't change, the intercurrent goes up. So we'll raise this back up to 10. And notice how good this is a pretty good simulation. It changed a little bit, but it went from 5.09 to 5.1, right? But the load current went up, so this had to go up. This guy's got to drop most voltage. This guy stays about the same. The intercurrent is constantly doing what? Varying its internal resistance to maintain a regulated voltage, which is pretty neat. Now, Zehners cannot give us a lot of current, but these very cheap little low current power supplies, the Zener would be the easiest way to go. And then we'll learn later on how we can add amplifiers that give us a current gain. Right? When we learn bipolar transistors, we'll learn how we can use the Zener as the reference voltage and let the transistor give us the big current gain to get a pretty good regulated power supply. But we're not there yet. So like that slick, this guy is dynamic, right? You understand. It's sitting there doing what? Constantly varying its resistance, trying to maintain a constant voltage across its leads. So normally we put normally we put the guy in there what? Reverse bias, right? Everybody understand that. That's when it's regulated. Right? Reverse bias. If I hook it up forward bias, what's going to happen? Nobody can guess? It's going to drop 7 tenths of a volt. It's going to act just like a diode, which means my load voltage will go to about 7 tenths of a volt. Notice that this guy now is dropping almost exactly 10 volts, right? Notice my input current and my output current are basically the same. Got a quarter amp to that thing. No, we won't drop the 7. So we normally operate these things in reverse bias, right? And they work in reverse breakover. Any questions? Guys, neat, ain't it? To me, it is. Might not be neat to y'all. So let's see if y'all can do this. So I've got a Zener regulated power supply. My input unregulated voltage is 30 volts plus minus 10%. I'm using a 1 in 47, 47. And my load current is going to vary between 10 milliamps and 20. So what things do we need to do? We need to calculate the size of the resistor, right? You understand that. We need to calculate the power rating of the Zener. When we say size, I'm not talking about the physical size. The ohms of the resistor. We need to calculate the wattage rating of the resistor, and we need to calculate the wattage rating of the Zener. First of all, what I'm going to do is I'm going to look up two things in my data sheet. What am I going to look up for my Zener? VZ. Well, we know wattage is 1, right? Okay. We're looking up a 4747. What's the VZ? All these are 1 watt Zeners. 20 volts, right? What's IZK? We need IZK because we're going to use that to calculate the resistance. Microamp. So what's my input voltage? 30 volts plus minus 10%. So 30 volts times 0.1, right? Huh? Would be what? 33 volts. Plus or minus. So we're saying, V in max is going to be equal to 30 times, 30 plus 30 times 0.1, right? Which gives us 33 volts. That's RMS, right? That's all we need here, RMS. Oh, wait, I'm sorry, this is DC. Then V in minimum, we need to know both of these. This is going to be equal to 30, right? Minus 30 times 0.1. So what's my minimum voltage going to be? 27 volts. Okay, everybody okay? I'll lose anybody. Yes or no? 30 volts plus or minus 10%. Isn't that what it says? Right? 30 volts plus or minus 10%. This would be my minimum input voltage. This would be my maximum input voltage. This would be my minimum. So my resistor needs to drop what? The Z is 20 volts there, right? Are okay? VZ is 20 volts. So my resistor is going to drop a maximum of what? The minimum voltage at the maximum current. So that'd be what? 7 volts. Okay. Over, what's my maximum? So R is equal to V over I. We want it to be the minimum voltage at the maximum current plus IZK, right? So, but what you got to understand, so VRS, this is what y'all probably need to do. VRS maximum is going to be equal to what? 20 volts minus, So this is probably another thing you need to get used to calculating. It's going to be equal to 33 volts minus 20 volts. So what's the maximum voltage VRS is going to have to drop? What's that? 13 volts. The minimum voltage VRS is going to have to drop. VRS minimum is going to be equal to 27 minus 20. So what's that going to be? 7 volts. So we went ahead and got that out of the way. So now we can use VRS max and VRS minimum. So we're through with these up here, right? We don't need those anymore. These are the guys that we're going to use right here. Okay, so what do we want RS? What do we want RS to do? We want RS to drop the what? Minimum voltage at the maximum current plus IZK. So so RS would be equal. What's my minimum voltage? 7. What's my maximum current? Load current? What's that? No, we're talking about the minimum current. We want it to drop the minimum voltage over the maximum load current plus IZK. So what's my maximum load current? I guess I should have wrote that down. 10 to 20 milliamps. Sorry guys, that was my fault. Is that right? maximum load current, right? So it's gonna be 20 milli plus IZK. What would y'all say? So many micrograms?
250 micrograms.
So what size RS do we calculate? Calculate the size. 300 watt? 150 ohms. What size are we going to use? This is calculated. This is not what we're going to use, right? You understand? We're always going to do what with this? We're going to round down to the next standard value, right? What's the next standard value? Probably got 3. No, we wouldn't go. We're always going to round down. We're not going to use it. 250 micro, yeah.
Yeah, so it'd be 345.
Three and what?
345.
Okay, that's calculated. That's not what we're going to use. So what's the next standard? What's the next standard value below 330? So I'm going to take 330. I'm going to multiply it by 1.05. Okay, so we can't use 330. Right? This came up to be what? 346. What's the problem? It's over that. We can't go over. We can go below, but we can't go over. So we won't use that. So what will we use? 300. And then we can use plus or minus 5. Huh? Oh, there is a 315? Oh, okay. I'm sorry. I knew that's going to be okay because this was only 1 ohm over. So I didn't, so that was only 1 ohm over, so I knew that. Okay, so 300 ohm. So what would we use? Now we got to calculate. So I'm going to come over here. I'm going to say what? V squared. So what's V squared? Our maximum voltage is going to drop is what? 13 squared over 300, Rich. What's that? 563 milliwatts. So we'd make sure we use at least a 1 watt resistor, right? Everybody okay? 1 watt. Can't use a half watt. 1 watt would work. We'd probably, usually what we do on this, just rule of thumb, is we double it, but we're just going to, okay, so what would the power of my Zener be? We was teaching this, I don't remember if we was doing AC or was we doing this class right here, but Dr. Crawford was upstairs and it really impressed him. Because he used to be a math instructor. Vice president. Dr. Ward is the president, Dr. Crawford's vice president. One of our vice presidents, we actually have 2 vice presidents. One of them's over business and one of them's over academics. So Miss Cruz, she's over vice president. She's over the whole business part of the college, and then Dr. Crawford's over the instructional part of the college. Dr. Ward is the guy. He's over the whole college. So what we got for Zen? Well, so what we got for here? So first of all, I'm gonna figure the maximum current that'll ever flow through this circuit, which is going to use this resistor. So the IRS max would be equal to the maximum voltage it would ever drop, divided by the size that we chose. 43 milli, everybody okay? So my power of my zener, VZ, is going to be equal to 20 volts, size of the zener, times the maximum current flow in the circuit minus the minimum current flow through the load. This is milli, by the way. So it's going to be 20 times 33 milli. What's that? Yeah, because that's the zener is going to conduct the difference between the circuit current and the load current, right? Understand that? 60, yeah, times 33. What do you got?
660 watts.
So 1 watt zener would be fine, right? Guys, y'all just designed the zener regulated power supply using Ohm's law, Kirchhoff's law, and Watt's law. So back in DC, you just did it with resistors, but you're going to find out even with bipolar transistors, our main formulas are going to be what? Ohm's law, right? Kirchhoff's law, and Watt's law. But we're going to apply it. What we're doing is we're applying it instead of a passive device. We're applying it to a device that's reactive, right? Understand that reacts to changes. Dynamics. And this is going to finish us up. So minus 3% the current. A 20 volt zener, 2010 milliamps, between 33 and 27 volts, right? That means that resistance is going to drop 13 to 7. We chose the 300. What we did in this class, I need to go back and correct that, guys, because this is 2%. The 2% would cost would cost a lot more than 5%, right? So I need to correct this slide. So y'all chose right. This right here would only work if it was a 2% resistor. I'll go back and change the slide. What do y'all think? Intense. We're going to give y'all, we'll look at this a little more, ask more questions, and then we'll be in the lab most of Thursday. We're going to give y'all out a worksheet. Probably what we'll do this time is let y'all work one of them. We'll work one in class, and then let y'all work the rest of them.
I like that.
That sound okay?
Yeah, I like that.
Okay, guys. Any questions so far? See y'all Thursday. I need to go back and redo those calculations.